Yes, actually, the punching shear capacity provided by GFRP bars, the slabs reinforced with GFRP bars is less than steel. And the reason is this: they have added a coefficient of 5K divided by 2 to the similar equation that we have for steel, which was 4 radical 5 F prime C BWD. B 0D. So this coefficient of 5K divided by 2 is kind of reducing the capacity of the concrete. And the reason behind this is it's considering the axial stiffness of the reinforcement. And as you know, the shear is the capacity of the strength is provided by 2 elements in the concrete. And the first is the shear is provided by the intact concrete. And the second is provided by friction between aggregates. So the intact part of the concrete reinforcement conditions is almost 1/4 and 1/5, or between 1/4 to 1/5 of the steel in GFRP. So having this in mind, we have a smaller shear intact concrete after the section is cracked for GFRP. For that reason, this formula of punching shear is reduced by the coefficient of 5K divided by 2. So, but according to the research, because of this friction of aggregates, we don't need to take the K value less than 0.16. So this kind of compensates this less amount of the intact concrete that forms in the GFRP bars. Now we don't have a table like similar the table that we have in chapter 8 ACI code for GFRP bars to directly apply sufficient thickness, so to avoid having excessive deflections, and also to avoid directly calculating the deflection for steel bars. So we need to control our deflection for GFRP bar whenever we design, until we get a similar table as we have in chapter 8. In my calculations in the presentation, I didn't consider the serviceability limited states. Just I wanted to give you an idea of the shear capacity, but for sure sometimes the serviceability limited states, they kind of controlling the GFRP behavior. So for sure, if you are gonna use this for real field applications, we need to check the deflection.